Hi, in this video we will learn about another indeterminate form, infinity over infinity. This is the second type of indeterminate quotients, and before we had 0 over 0, and we know that to resolve it we need to do L'Hopital rule as a general rule, and we'll see that L'Hopital rule also works for this case. Well, let us start when this thing happens. Well, we have two functions, f and g. Their limits as x approaches to a is equal to either plus or minus infinity. It can be any combination, plus in numerator, plus for f, minus for g, and so on. Then the quotient f of x over gx, when we find the limit of the function, the quotient as x approaches to a, then we get infinity over infinity, which is not a number, and actually it should be resolved. So f and g are growing either in positive or negative direction, and now we want to see what is the ratio, which one is growing faster with respect to other one, or what is the ratio at which these two functions are growing with respect to each other. Well, this is called an indeterminate form of type infinity over infinity. Okay, well, we actually already seen these cases. For example, when we have rational function as an example, this function x squared minus x plus 1 over 3x cubed plus 2x plus 1 as x approaches to plus infinity. Well, remember that in these cases that we have right away, you can see that we have infinity over infinity. We had a way to resolve this infinity over infinity by factoring the highest power from the numerator and the denominator. So it will get 4 plus 2 over x minus 1 over x squared plus 1 over x cubed. And in the denominator you get 3 plus 2 over x squared plus 1 over x cubed. And before even you find the limit, you can cancel this common factors, and you see that as x goes to plus infinity, these guys go all to 0. 4 stays the same, and this and that will go to 0. As a result, we will get 4 over 3. This trick only works when we have rational function, a polynomial over polynomial. What about the general indeterminate form of type infinity over infinity? For resolving these cases, we have again L'Hopital rule, which says, okay, if f and g are differentiable, and well, we can write what is f prime of g, f prime over g prime. It means that f prime is non-zero in an interval around a. Then we also know that f over g gives us indeterminate form if a limit of f of x as x approaches to a is plus or minus infinity, and limit of gx as x approaches to a is plus or minus infinity. Then we have the indeterminate form. Yes, a limit of f of x over g of x as x approaches to a. This will be equal to limit of a new function, which in the numerator has f prime, the derivative of the numerator, and in the denominator has the derivative of the denominator. And as before, remark, the above trick or the above L'Hopital rule is true when we have one-sided, so x goes either to a plus or minus, and for limits at infinity. So you can find the limit of indeterminate form infinity over infinity by applying L'Hopital rule. You turn it into another limit, hoping that that limit is easy to compute or can be evaluated with some tricks. Okay, so let's see some examples now. Okay, so the same limit as before, polynomial over polynomial, and right away you see that it's infinity over infinity, and well, all the conditions are there. We can use L'Hopital. And what is the L'Hopital saying here? In this case, it says, well, find the derivative of the numerator, 12x squared plus 4x minus 1, and the derivative of the denominator, 9x squared plus 2, as x goes to plus infinity. These two limits should be the same thing. But this limit itself is also infinity over infinity, so I can use L'Hopital again, and this time I get 24x plus 4 and 18x as x approaches to plus infinity. And again, another time we get indeterminate form infinity over infinity and use L'Hopital rule another time. And what we get is limit of 24 over 18 as x approaches to infinity. And that gives us 4 over 3. Well, just a nice check now. You see that before also we got 4 over 3 here, and this gives us 4 over 3 again. Very nice. Let's do this other one. Limit of ln x as x approaches to 0 plus. Well, let's just for a second look at the graph of ln x. Ln x has a graph like that, yes. As x approaches to 0 plus, the ln goes to negative infinity. So we have negative infinity in the numerator over. In the denominator, however, we have what? Cosecant is 1 over sine x. 1 over sine x as x goes to 0 is 1 over 0, so it will give us a plus infinity actually. So we have indeterminate form of type infinity over infinity, and these are nice functions. We can use L'Hopital's rule. And well, means what? Means that we can replace the derivative of this limit by another function, which is the derivative of numerator, 1 over x, over the derivative of the denominator, which is what? Cosecant x times cotan x, as x goes to 0 plus. Well, here, as you see now, I have in the numerator infinity and again another infinity in the denominator. But the best way to deal with this now is that if you continue again using L'Hopital rule, you will get again harder and harder function. What you need to know here is that I can simplify this guy. I'm not taking any limit. I'm just trying to simplify. Cosecant x times cotan x. That will give us cosine x over sine squared. There's a minus sign there. And there is 1 over x. Let us turn this one a little bit, make it one fraction. So fractions of fraction, I want to make it a fraction. So limit of will be sine squared x over minus x cosine x as x approaches to 0 plus. Here, well, again, you can do different tricks. What I like here to do is to go ahead and see that, oh, this is 0 over 0. This time I have indeterminate form 0 over 0, and I can use L'Hopital's rule. And this will give me 2 sine x cosine x. In the denominator, however, we will have minus cosine x minus x. The derivative of cosine is minus sine, so we'll have minus sine. You have to be very careful while doing these computations, because all the time you have to make sure that you get something that is a number or an indeterminate form. In this case, you see that limit of the denominator is minus 1 plus 0. Limit of the numerator is 2 times 0 times 1. So I have 0 over negative 1, and that gives me just 0. So I had negative infinity over infinity. I did L'Hopital, turn it to 0 over 0 indeterminate form, and then applied L'Hopital's rule another time, and I got 0 there. Well, okay, let's do this one right away. As infinity, obviously, ln of x as x goes to plus infinity is plus infinity, and x itself as x goes to infinity is infinity. So then we can use again L'Hopital's rule. And this time what we'll get is 1 over x, 1, as x goes to plus infinity. And that is limit of 1 over x as x goes to plus infinity. And that is another 0 there that we were looking for. Well, how about this one? Okay, e to the power x plus 3x. This is plus infinity, and this is a polynomial, so it will be again plus infinity over plus infinity. Then limit of this, I can use L'Hopital again. Well, for the first time for this example, this will be e to the power x plus 3. In the denominator, you get 2x plus 2 as x approaches to plus infinity. Again, you do it again, you see that we have indeterminate form infinity over infinity, and we can use again L'Hopital's rule. This is limit of e to the power x plus 0 over 2 as x goes to plus infinity. Now, I have e to the power x infinity divided by 2. Infinity divided by any number, non-zero number. Well, actually 0 is even better, but you have a big number, you divide it by 2, and it is again another big number growing bigger and bigger. So this will be plus infinity. Yes, it can have infinity value, but the point is that L'Hopital rule goes showing that this limit is equal to that, this limit is equal to that, and that limit we know that is plus infinity, and that's where we get the limit of the original function. So infinity over infinity is another indeterminate form from the quotient indeterminate forms, and to resolve it you can use L'Hopital rule, and it works nicely.